Well, looks like it is past time and ready to get started. So, I shall get us started with the last chapter of thermodynamics. For better or worse, we've come to this last chapter. And so, I'll introduce it and actually try to get through most of the material. I think we will. Chance that we get through all the material. But the reason I say that is because you have a test coming up pretty quickly. And it would be great if we had gotten through all the material so that then next Tuesday could just be a day of doing example calculations. And that means you wouldn't have any new material given to you on Tuesday that then is going to be on the test on Thursday. Although I don't think that can quite happen. There's kind of going to be a last little step. But certainly most of it's going to happen today. All that is to remind you, you have a test coming up. It is next Thursday. And it is on thermodynamics. And it will be a good time to just wrap everything up as we go into spring break, because we will shift gears again. So hopefully, although it might be a little busy and stressful between now and next Thursday, you'll be ready for spring break by the time it gets here. And you won't have to stress about this class. You won't have anything really to do unless you're looking ahead, because we're going to shift gears. So this is our last chapter on thermodynamics. When we come back, we're going to do our first chapter on optics. And so we're changing gears. Now, all that is to also add here, before I pull down the screen, to remind you that this Sunday, Don set up a review. So as you know, I always like to do a review as the test comes up. So besides today's lecture and Tuesday's lecture, you have Friday, tomorrow, MC, and then you have a Sunday additional MC that, like I said, Don has scheduled for you. 17th, I guess I just noticed that's St. Patty's Day. Tell Don to bring some green beer. And then from 1 to 4 and right in here. All right. All right. Well, I'll pull down the screen. Maybe it's a little early to pull down the screen, because what is this chapter? What is being covered here in these last steps? And so chapter 22 spends most of the time discussing heat engines. And that's where I want to spend most of the day. From there, that will lead into entropy, so that'll be something new. And entropy, as we will see, is the second law of thermodynamics. And so this is where we will stop our study of thermodynamics with the second law and entropy. And like I said, an important step here, and like I hopefully will set the stage here for an understanding of entropy, although that's probably about where we will leave off on entropy as we leave today and come in till Tuesday. The heat engine part is hopefully self-explanatory. It is what I've been talking about here. So let's take this next hour and just kind of look at, now that we've done really quite a bit of thermodynamics, how can we use them to actually build things that move, make a factory, build cars. And so you have watched this a couple of times already. But now you're actually ready to do the math. Now you're actually ready to understand the mechanics, both on a macroscopic and a microscopic, and calculations to figure out how much energy and how much work this engine will do. Here's why we call it heat engines. You've watched me do this before. You say, okay, if I have a set of gas with some weights on it, and if I put it in some hot water, or I heat it, like burning gasoline or diesel fuel, or however I heat it, it can push. It can do work. And if we were lifting a bunch of weights, we might say, okay, we lifted the weights off, we'll put them there. Then, after you've lifted the weights off, you can kind of reset the machine, if you will. You can cool it back down. Or in the case of our engine, we will open a valve and we will let the burnt gasoline out and start anew. So then, if we had another set of weights, which I don't have another set of weights, so I'm going to pretend these are new weights, and I can put them on my engine, and then I can heat that up again. And so I already lifted 2, now I lift 2 more, and so I can move these to the next level here. And so if I was lifting things up a building, maybe this is construction material as I'm building a building, or some of the first heat engines were designed to lift bales of hay up inside of a very tall barn, and the farmers would come out and put it in the fire, lift up the bales of hay, reach out the window, pull in the bales of hay, take the device and throw it in a bucket of water. And as it would throw in the bucket of water, the little elevator would go down. And as it would go down, people on the ground would put more bales of hay. And then they would toss it back into the fire. And they tossed, yes. And so this is kind of the first design and the first performance of a heat engine. Obviously, that's a little slow to make a car going. So people quickly realized that you could probably make this go faster if you didn't wait for it to cool down, but you just opened a valve and let the hot stuff out. And then if you just let the hot stuff out, it does go down pretty quick. And that's what we're going to see in our real engines, like a steam engine, like a car gasoline engine, like a truck diesel engine, like a Stirling engine, like a 2-stroke chainsaw, and so the Mazda rotary engine. And so we'll look at a couple of those, all of those actually, in the next hour here. But there is the mental picture. Energy goes in as heat, it does work, and then you reset it by cooling it down. If I were to draw a picture of this, it would not be all that impressive looking picture, but here is going to be our diagram for an engine. Ooh. So without really going into the mechanics of how the engine is built, and that's why I kind of like to have this and some animations that actually show you the real internal mechanics of how an engine is built, our thermodynamics is just a discussion like this, is that what you have is you have something that is hot. And what you do is you feed in Q. I'll call it Q sub H. Energy flows in. And so our diagram up there hopefully looks like this to you. There's the Q sub H. And so does this look like that? Say yes. All right. And that's our diagram. So this is our diagram in terms of energy. This is our real mechanics of how the crazy thing is built. And then all the internal parts of the engine are here. And here's the purpose of the engine. The purpose of the engine then is to do work. And so this idea here is we put the heat in and we get some work out. Now let me ask you a couple questions. First one, can I ever have this scenario? Can the work I get out be greater than the heat I put in?
Never.
Why not?
Unless you pull some temperature somehow, but I can see that happen.
Okay, so you're right. We have certain restrictions, don't we? We have, what you said, the first law of thermodynamics, conservation of energy. And I want you to realize that, hey, right away, you could never have more energy coming out than you put in. That would be a violation of conservation of energy. Fair enough? Could I ever have this? Could I have the amount of work equal to there? And so I brought this out here. Not that it's that exciting, but we really had the same discussion back in Physics 121. We had something that, if it's level, which it does not look like I have it level, and my little legs are there, and this one doesn't quite fit on here. All right. But back when we did our mechanics, we really had this same discussion. We could ask this simple question, the conservation of energy one. That is, if we were to take a moving car and collide it into another moving car, can that car go faster than that one if they have the same mass? No, why not? Yeah, it would take more energy. That one would have more energy than that one. And we would say, oh no, you can't do that. Conservation of energy. And again, I would say the same thing here. I could not have more energy come out than heat I put in. So the best I could do would be this, right? At least according to the first law of thermodynamics. But again,
what about if you got enough heat to activate a chemical reaction?
okay, well, and I should make that obviously very clear that without adding extra energy, because we could, okay, fine, I could add heat here, and then that one can be greater than that one because I've got one and I got two. So, yes, I could make it go faster if I added energy from another place, right?
No, I mean like if you had a chemical that was in unstable equilibrium.
Yeah, and then you burn the chemical.
Then you're getting more work out than you put heat in.
Well, no, because I would count the heat in as the energy of that burning chemical that you're talking about as being unstable. Make sense? Okay, so I guess what I'm trying to say is this right here is accounting for all the energies. The heat I put in, if I put it in by hot water, plus this unstable chemical that burns, maybe gasoline, but I'm putting all those together, and then there's no way I can get more out from there. Okay? All right, let me turn this around. Because again, we had exactly the same discussion in mechanics. If I turn them around and it sticks, can I make these move along, stick together, and have no heat created in the process?
Are only one's moving them?
And I better not spend too much time here because I don't want to get bogged down in mechanics. But I do want to realize or have a discussion here that when I have two things colliding and sticking together, is it possible for those two stuck together to have the same kinetic energy? No. Why not? What else is going on here in this collision? So, if I said 1/2 mv1 squared equals, then they stick together, so let me call that 2m, and some new speed squared, and then maybe there's heat, maybe there's not, and that's really my question, right? This is conservation of energy. This is how much kinetic energy does it have before the collision, has to equal to how much does it have after, plus any heat that's created. And my question is, could I have no heat?
You would need to have really.
And if you say no, I'm saying why? Because if we had no heat, couldn't this speed just be low enough so that the energies are the same? Yeah.
Does the impact of one thing hitting the other one, they do it opposite, equal and opposite reactions with both little trucks things. They both apply an energy to each other, but isn't some of the energy internalized as the wind?
We have a lot of laws of physics, right? And you have just told me earlier on that I cannot get more work out than I put in because of conservation of energy, right? And I totally agree with that. But I also want you to see that in a given collision, there's not just the issue of energy, there's also the issue of momentum. You forgetting that one? And if I go through this math, we learned that not only momentum has to be conserved, but energy has to be conserved. And if they stick together, then the velocity of number 2 has to be half of the velocity of number 1. And if you put that into here, then this 1/2 mv1 squared, which then equals 1/2 2m v2, which is now 1/2 v2 quantity squared plus q. It is this right here that comes out to be 1/4 m v1 squared. And I told myself I wouldn't do this much math because we got a lot to do. But I want you to realize that we have been doing conservation of momentum, we've been doing conservation of energy, we've been doing conservation of angular momentum, and all of those principles tell us what can and cannot happen. Fair enough? And so back in 121, we learned that there is no way you're going to have two objects of the same mass sticking together and creating no heat. It's impossible, right? Because in order to conserve momentum, you have to have this speed. And if you have this speed, you don't have enough kinetic energy. And so therefore, the heat that is created in the process must equal to this number. There is no way two objects can collide together and stick and not create any heat. It is mathematically impossible. You cannot conserve both momentum and energy at the same time. Fair enough? Now, let's get away from our mechanics and add to this, because you already told me this can't happen. Why? Conservation of energy. And I'm asking you, can this happen? And I would suspect that at this point in your education, you're going to say, I can't see any reason why not. But there is other things going on. And that's what this example was supposed to illustrate. Not only do we have conservation of energy, but we also have conservation of momentum. You have to obey each of the laws of physics in order for those to work. And what you have not been introduced to yet is the fact that there is something else going on. And so just like in our mechanics we dealt with the energy and momentum, when it comes to thermodynamics, we are going to deal with not only the energy but also a quantity called entropy. Symbol S. And it is this extra piece, which we will call the second law of thermodynamics, that we will say the same thing. We will say what can and cannot happen. Maybe you see it best if you do these density blocks. I brought these density blocks out again to just kind of illustrate the same basic principle. Let's say I heat this one really hot and this one cold, and I stick them together. If I draw a picture of that, it would look something like this. Here is the first block that is hot. Here is the second block that is cold. We've done this many times. What do you think would happen when you put a hot one next to a cold one? All right, there is a flow of energy. We've been calling that Q. Fair enough? Now, if I were to ask you, the Q coming out of the hot one, how does it compare to the Q, and I'll just do magnitude, going into the cold one? They're equal. And you would say why? Conservation of energy, right? Couldn't be more, couldn't be less. We have certain laws of physics that have to be obeyed, whether they be momentum, angular momentum, energy. We know that those would have to be true. Couldn't be more, couldn't be less, right? All right. How about this? Could energy come out of the cold one and go to the hot one? I mean, I'll keep them equal because I don't want to violate conservation of energy. No, 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 no. I'm sold on that one. So, can I put two blocks together and the cold one gets colder and the hot one gets hotter? I can't?
It's a random chance.
Why not?
Like small.
The hotter one
If you had a
has
machine.
more energy. Like the molecules are moving faster.
Sure.
So, and the cooler.
So,
the
so
reason the cooler one gets hotter is that some of that motion is transferred to that.
Oh, yeah, okay. So some of the motion goes from here to here, right? But why can't these just, I don't understand why these can't slow down and these speed up.
Isn't there a random chance?
They have to hit each other. And the other ones are really fast. Wait.
Oh, so there must be something else I need to think about besides just the energy. Is that what you're trying to tell me? You're telling me it's the random chance. You're telling me if the hot ones are going faster, they're more likely to hit the slower ones and make the slower ones go faster. It is highly unlikely for the slower ones to catch up to the fast ones and hit them. Is that what you're trying to say? Right? So there must be a reason why this doesn't work, right? And see, and it's not conservation of energy. It's not conservation of momentum. It's not conservation of angular momentum. It's not Newton's first, second, or third law. What are you're telling me it's what? Statistical random chances? Is that what really you're saying? And yes, that is the part of the puzzle we have not dealt with when it comes to thermodynamics. There are more principles than just conservation of energy, conservation of momentum, conservation of angular momentum, Newton's 3 laws of motion. There is also statistical chances and probabilities, and that is what we need to learn in this chapter. The second law of thermodynamics. The second law of thermodynamics has to do with this thing called entropy. Entropy is this statistical chance of things happening or not, yeah, I guess it would be the same kind of thing. It would tell us what could and couldn't happen. But the way it happens is not based on a quantity of energy, not based on a quantity of momentum, not based on a quantity of angular momentum, but it's based upon chance. Random chance. And that's where I want to begin the chapter. That there is more than just energy going from here to here. There's also this thing called entropy. Now, we have yet to develop it, but we will soon see that just like momentum was a product of two things we already did, mass and velocity, just like kinetic energy was a product of things we'd already have done, mass and velocity squared, entropy is going to be a useful idea and a useful quantity. And it is the quotient of two things we've already dealt with. The heat and the temperature at which that heat is being transferred. So I will call this TH. But now, maybe you can see a little bit more of what the second law of thermodynamics is going to do for us is when we go to ask what can and cannot happen, we will have to say this can't happen because of conservation of energy. But we will also say this can't happen because of the second law of thermodynamics. And I know I haven't developed it yet, but I'm trying to set the stage of what is the second law of thermodynamics. And it is called entropy, and it is just random chance. Statistical probabilities. Yeah.
If it's random chance, doesn't that by definition mean that that can happen?
Oh, very fair enough. And so entropy, I think, is one of the hardest, and the second law of thermodynamics is one of the hardest things to really pin down. We're going to try that. If we get that far today, I've got 6 pennies up here. And entropy is like these 6 pennies in this sense. Is it possible for me to get 6 heads? It's possible but unlikely, right? So entropy is a lot different than, say, forces and energy because it is, as you said, a statistical chance. There is nothing saying I can't get all heads, but I won't. I wish I could, but I won't. Now, this is only 1 out of 64. Okay, but fair enough. Let's change this to the atomic size, and I have billions and billions and billions of atoms. This is only 2 to the 6th. What if I had a billion pennies and I threw them up? What are the chances of getting all heads? 1 in a Billion, 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 billion. Anything stopping me from getting all heads? No. Will I ever get all heads? No. There's still a chance. And again, you're going down the right road, that this whole idea of the second law of thermodynamics is really another law that tells us what can and cannot happen. But it is a little different. It's a little different than anything else we've dealt with. This is just statistical chances. So, hopefully between now and next Tuesday, we'll just throw this a few times and see. Heads, tails, 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 heads, tails. Nope. Should I try it again?
Yeah, see all tails.
Heads, 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 tails. Tails, 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 heads, heads, heads. Well, we'll keep throwing it out through the day. Maybe we'll get lucky.
Maybe find an automatic factor or something.
To carry the billions of pennies analogy a little bit further, is the random chance you're talking about like the idea that it's really unlikely that if we had a billion pennies that they're all going to end up on heads, but compared to 100 pennies versus a billion pennies, we'll end up on average with more heads up.
All right, so
Not out of the group, but
more to try and just kind of plant the seed here for the second law of thermodynamics. To tell you that we're going to deal with this heat engine, but when we deal with the heat engine and we deal with what can and cannot happen, we need to look at not only the energy, but also entropy, okay? So let's try this for a moment. You already told me that you have never seen a piece of ice get colder when you put it in a room, right? Could it happen? I guess statistically it could. But as we sit down and do the calculations, what are the chances of a slower moving one coming along and hitting the faster moving one? And this happening again and again and again, billions of times, so eventually the hotter one is hot and the colder one is cold. Could it happen? Yeah, I suppose. I could win the lottery too. But I have a much better chance of winning the lottery than I do billions and billions and billions of times more chances of winning the lottery. And I haven't won the lottery yet, so I doubt if I'm ever going to see this happen. Well, let's try this one. Here, I have a bunch of atoms and they're moving, right? They're bouncing around, all right? Now, how many atoms do I have? Well, I happen to know this is aluminum. I know up here that aluminum has a molar mass. Where is aluminum? Oh, about 27, okay? Now, this then is about 3 moles worth of atoms, all right? So there's a lot of atoms in here, and each of them are moving, fair enough? Bouncing around, ricocheting. If I were to calculate how much energy they have, I might do something like this. I might say, all right, N, CV, and I'll just put a T, and say this might be a rough calculation. And again, take this as a rough calculation for the energy. Because first of all, we derived this in the last chapter, but it was really only true for a gas. Do I have a gas? No. All right, but maybe if you thought of this as a gas, then it would be more valid. But even then, we said CV changed as you changed temperature. But again, so don't take this too literally, but it does illustrate my point well, is that if I were to figure out how much energy is actually in this block of metal right now, because of the motion of the atoms, I would come along and say, well, this is 3 moles of aluminum. I'll just take them as monoatomic. Again, not, don't take it too literally here. But I would say that their energy is given to them because they warmed up from absolute 0, let's say, so they were stationary, and I warmed them up and I warmed them up, and so now they're in this room at about 300 Kelvin, maybe a little bit lower than that. So how much energy is that? Well, let's see. This is this is a bad example. Let's change it. That's going to be so far off. Let's do degrees of freedom. Let's do that. All right. So let's say 1/2 kT. Let me do that. That's what I would get for every degree of freedom. All right. So then let's just say that they have 3 degrees of freedom. We might argue that there's 6 because not only can they move X, Y, and Z, but they get potential energy X, Y, and Z as they move closer to them. And but I won't bicker about that one there. But this then would be the energy. Then I would multiply it by 3 moles. And that's, I guess, what I really meant to do there. And so each atom has about that much energy, and I have that many atoms. So 3 times 6.02 times 10 to the 23rd times another 3 times a 1.38 times 10 to the negative 23 times a temperature of about 300. And what I'm trying to get across is you might be surprised at how much energy really is inside of those moving atoms. And if you could harness all that energy and you could say, look, let's take all that energy and let's lift it up. How high would it go? Well, again, 3 moles. Well, that would be 3 times 27 grams. And then G would be 9.8. And so that little block of aluminum, because of the motion of the atoms, has the ability to go up 28,257 meters. Which, of course, this would be an inappropriate calculation to even use when we get that high. Maybe not, that's not too high, but this was inappropriate. But my point really is about entropy again. Do you see how much energy is in here? So, is there enough energy for this to jump up and hit the ceiling? Right? Will it jump up and hit the ceiling? Have you ever seen it jump up and hit the ceiling? And so what would you answer when someone said, why can't that thing jump up? Doesn't have enough energy? No. Heck no, it's got plenty of energy. Why can't it jump up? What would take it to jump up? What if all these atoms were all moving up at the same time? What would happen? It would, right? So all I have to do is wait long enough for all those to go in the same direction, right? But how come I have never seen a car in the parking lot just jump up a few hundred meters? How come I've never seen a block of wood just jump up a building? Isn't there enough energy for it to jump up hundreds and thousands of meters high? And yet it never seems to happen. Why? The statistical chance of all of those molecules going in the same direction at the same moment. It is just highly, highly unlikely. So is anything stopping this from jumping up there? And so we're going to say, yeah, the entropy of the situation is. The second law of the thermodynamics is. This will not jump up and hit the ceiling because it lacks energy. It has plenty of energy. What it lacks is, you might say, organization of getting all these millions and billions of atoms going in the same direction. And so again, kind of corny, I know, but it's my way of saying, look, we've got something else going on here. Besides the first law of thermodynamics, we have the second law of the thermodynamics. And it too will tell us what things can and cannot happen. And it's a little different than any of the other ones we've seen. It is not a conservation of energy, a conservation of momentum, a conservation of angular momentum. It's just the statistical chance. Like I said, it's like there's nothing. There's no magical force stopping me from winning the lottery. It seems like it, I know. It seems like that thing can't go up there, I know. But there's nothing stopping it, it's just highly unlikely. And then week after week, I keep shelling out the $5 and I'm still losing, right? And it's even sadder when I look at the statistical numbers and realize that my chances are higher that I get hit by a falling airplane part than I do from winning the lottery. So I'll probably get killed by a falling airplane part before I win the lottery. Darn. But somebody's got to win, right? I'll keep trying. I'll keep spending my college, or my kids' college tuition. They don't need to go to college because I'm going to win the lottery. All right. But it's just not going to happen. I'm not going to win the lottery. That's not going to jump up.
So if it actually did jump up to that height, would it then have a temperature that was zero?
Well, yeah, yes, and then it would have to lose its energy, just like a baseball going up, it loses its kinetic energy. If I could get all those going up, as it would go up, it would be this high with a temperature of 0. Then it would come back down and make all the molecules go fast again and then be back at that temperature. Mm-hmm.
So you said this wasn't like any other type of law we've done before, that it's its own separate thing. And I was thinking, like when you stop a car, like the molecules don't change. And I was like, maybe that's a bad example, but like if I slap my hand on this table, all the molecules on the surface of my skin are all being at least pushed in the same direction back by the normal force of the table, right?
For a moment, and then they bounce and ricochet off, and now they're in random motion, now they're heat.
But they're all actually pointing in the same direction at that point. There's no thing I'm missing. It just happens to happen out really quickly.
Oh, yeah. Remember, they're hitting hundreds of trillions of times every second. Right.
Isn't it not just probability, but actually impossible for them all to go in the same direction without outside force? Because they have to bounce off something.
Yeah.
So you can't just, send them just automatically up without an external force.
So, let's see, how do I answer that? But I guess okay. So what you're actually adding to this argument of the second law of thermodynamics. What you are saying here is that these are already in a random motion. Okay, in order to get them to go all up, I probably could. They wouldn't just statistically do them on their own, but they might, if I were could put little tiny reflectors in here and angle it just right and put in a lot of effort, then I may get them all to go up. But I claim in the process of doing that, I get them up. I have just made a bunch of other molecules. I have also have a bunch of randomness created. So I have a lower randomness to this, but a higher randomness to something else, and the total randomness never increased. And that's what we're going to see.
But then, so by itself, statistically, it's not possible. It's just if you alter it, then it's possible.
Oh, if I alter it, it's possible. Sure, if I put in some extra effort. And that's what we're going to see here, is that anything that we say is impossible to do, what we mean is just on its own. Right? We could make this go up really high, but we have to do something to it. And in that process of doing something to it, the molecules we work with will be just as random as those once were before we tried to straighten them out. Okay? So, if you want to use this as an excuse, if your roommate asks you to clean up the dishes, wait. If I clean up the dishes, they'll be organized. But the molecules in my body and the heat that's created are going to have as much or more randomness. So there's just going to be just as much randomness in the universe, so why do the dishes? Say that again, I can't quite hear.
If you put that block of aluminum in a magnetic field, it's
Right.
strong enough to point all of its atoms upwards, but you can defy gravity. Is that
Okay, but well, first of all, aluminum's not magnetic, so.
trains that levitate on the rails?
Yeah, but okay. But that's an external force. That's a magnetic force. So I would put that in the same category of, I could lift this up to the ceiling, sure. You know, I could come and push it with my hand. I could use a magnet to push it. Yeah, but due to an external force, right.
How in the world do you measure entropy anyway? It's
Ah.
randomness.
Okay, so as you can see, this is going to be one of the harder principles that we have. I think visualizing velocity was probably the easiest thing we ever did so far in physics. You have a car and you go, look it took a long time to get over there. And you have a visual picture of velocity. Momentum was maybe a little harder. Momentum and energy, you can't really see with your eyes, but because they're related to speed, they're not quite so difficult. You see a car moving along real fast and you go, well, that has a lot of speed, probably has a lot of momentum. But really, maybe not. It could be a heavy car or a light car, right? You could have a light car going really fast and a heavy car going slow and still have that slow car having more momentum. So it's a little bit harder to see, I think, conceptually, what is momentum. Momentum and energy are a little more abstract. And entropy is probably the most abstract of all. It is randomness on a microscopic level. And so, if we heat something up, we'll just say they're bouncing around a little bit faster. Does that kind of fit the picture? That they would be more disorganized? And so that's what I will be asking you to do before the day's over. Think about the motion of those molecules. Anything that we heat up is going to then have more random motion. Anything we cool down, less. Anytime we put something in a box and we let the box get bigger, that means these molecules can spread out more. That is more disorganized than if they are in a small box. And so the entropy is related to that. Well, anyways, I better keep going on. I didn't mean to spend quite this long on just kind of setting the stage and getting you ready for the entropy, but that's what I wanted to add here. It's not only heat that goes into this engine, but it's entropy. And so coming back to my simple example here, when I did this and I cooled it down, I want you to add to this mental picture. When I put this into here, what's going in here? Heat and entropy. There is two quantities going in here. It's not just heat. There's also entropy. Yeah. Oh, absolutely. So, I didn't really prove this to you, but this is going to be our equation for entropy. Entropy is going to be the ratio of heat out divided by the temperature that you take it out. So when I was performing this little bit of experiment here, I put it in here and you saw heat go in and entropy. Or at least I'm hoping you kind of have this mental picture. Two things are going in here. First law, second law. Energy and entropy. And so then, when I do this, what's what happens? What comes out? Two things, heat and entropy. And so, I will put two arrows coming out to my cold container. The one I hope is obvious, heat comes out. But the other one is not so obvious, entropy. That's the new piece of the puzzle for chapter 2. And look what this actually says then. It says entropy is related to heat. Makes sense why we never even mention the word entropy in Physics 121 or in electromagnetics. It has to do with heat. It has nothing to do with the mechanics. So when we did our mechanics, we did Newton's 3 laws of motion. We did conservation of momentum. We did conservation of energy. We did conservation of angular momentum. We didn't say anything about entropy. It wasn't needed. It wasn't part of the puzzle. It's only part of the heat puzzle. So that's why we have it now. That's why it's the second law of thermodynamics. It also says this. Notice it says then, if you put entropy in, if entropy can't come out as work, then there is no way that all the heat that comes in can go out as work. Why not? Because how are you going to get the entropy out? What do you need? You need some Q that comes out. It is unfortunate. The world would be a much better place and things would run a lot easier if I could get more work out than I put energy in. That would be fantastic. It would be great if I could just get out the same work that I put energy in. That would be great. But it wasn't for this stubborn entropy thing. I could, but I'm trying to say is I can't do this, first law. I can't even do this, second law. What has to happen is that. That's the only option I have to me. The workout is always going to be less than. Bummer. Can't even build a good engine. Right? Now, with that in mind, I can build the best engine that nature will allow me. So using the first and second law of thermodynamics, how close can I build an engine to that? And the good news there is we've got a long way to go still. So you've got plenty of room for your development and your energy, make lots of money, big bucks, donate back to the school, you know, fix our tile roof, buy us new computers, remember where you got started, remember your physics teacher, he likes his Ferraris red. All right, so there's still a lot going on here, but this is a very important part. Second law of thermodynamics. It says again, like any other of our laws, what we can and cannot do. All right, so keeping that in mind, you realized now, with not any proof, but the second law of thermodynamics tells me this is not just going to all of a sudden just jump up out of nowhere. It also tells me when I put a hot and cold object together, the energy never goes from the cold over to the hot. It always goes from the hot to the cold. It's a statistical chance, but that's all that can ever happen. It also tells me, unfortunately, that when I go to build a real engine, the work that I can get out of my heat engine is the difference, and I'll put them in absolute values so that I don't have to worry about the pluses and minuses, because I know when heat goes in it's positive and when heat comes out it's negative, so I'm going to just think of this in absolute values, and I think it's a little better, and your author thinks of it that way too. But there would be an equation that would say how much work is being performed. And it's because of this second law of thermodynamics, it's because of this entropy that we are stuck with the unfortunate reality that this number will always be less than that number. Because we have to have this number. We have to have that number because that's the only way we can get entropy out. Entropy can't come out through the work. Okay? And that's the first section of this chapter. What is going on? Both first and second law of thermodynamics have to be obeyed. So we like to do this. We like to ask ourselves, okay, if you're going to build an engine, then how efficient is it? You just told me that you're never going to get all the energy out. I would call that 100% efficient. So we're not going to have that. Fair enough. But I may make it 90% efficient, 80, 30, 10, 5. Hopefully I'll do better than that. But I think real engines operate, you know, like 25, 28% efficiency. Okay? And so most of the heat energy is not used. Now, part of that reason is I can't use all the heat energy because of the second law of thermodynamics. But the other parts of it is I just don't have the best designs in the world. And so what else could I do to it? And so what we will do is we will talk about the efficiency. And the efficiency is defined this way. How much work do you get out compared to how much heat you put in? Kind of make sense? And so it's kind of your standard definition. In fact, if we kind of look at these two together, you will see then that the heat put in minus the energy taken out, cold, would be the work. If we divide that by the heat, and I'll just put everything in absolute value so we won't worry about pluses or minuses, energy going in or energy going out here. What this comes down to is then the efficiency of an engine is this ratio. And so this kind of tells me that depending on the process, because remember, Doesn't the heat coming in hot and the heat coming up cold, doesn't that depend how it is? Did it come in an adiabatic? Did it come in an isothermic? Did it come in an isovolumetric, right? There's different processes. So depending on how we build the engine, we would calculate heat differently, right? And so some engines will end up being more efficient than other engines. But you can kind of see that the big picture here is to make something as efficient as possible, we would want the cold to be as low as we can and the hot to be as high as we can. Of course, there's realities that come into play. I mean, how cold can you get this? Well, the easiest is, of course, just to burn something, and the cold side is just the atmosphere. That's kind of like the engine in your car. You just, hey, let's just let it out to the atmosphere. All right. And so that is our low. And our high is the gasoline we burned. If we wanted to make it more efficient, maybe we should burn something other than gasoline, something that burns a little bit hotter. Now, hydrogen is a good example of that. And so I can make this a little bit hotter. Problem with that is, if I get it too hot, what happens to the internal parts of this car? Yeah, they get weak and break or melt if they even get hotter than that. And so I'm stuck with the reality of the cold and the hot. And if it is a power plant of some type, maybe I can set it near the beach and I can get the cold water from the ocean to come in. I can put it up on the Oregon coast, and that might make it a little bit colder than the air. Oh, that'll help a little bit, right? Or near a river, a cold river in the Northeast. And so that will help my efficiency. You know, maybe I can make better materials. I can burn it hotter. But I think you're getting the idea here of the idea of the efficiency. Yeah.
So when you said the car is running at 25%, could you just guess then that ratio of QC over QH is 75% or 3/4?
Oh yeah, exactly. So three quarters of this. And again, engines can vary significantly. So.
Factor though that makes them 25%? Is there something else other than this that makes them not 100%?
Well, okay, don't underestimate. You say other than this. I guess I'll answer that by saying no, but how you burn the gasoline. Do you burn it with constant volume? Do you burn it with constant pressure? Do you burn it? These numbers are calculated differently depending on the processing. Okay? So I'm glad you asked, because that's where we want to get started. Let's actually look then at a real engine. We'll calculate the efficiency of a couple of engines. If you're not familiar with the internal workings of a four-stroke engine, let's look at this little diagram. Here is supposed to be a little picture of what is going on in what is called a four-stroke engine. And in this diagram, you will hopefully see this. This here is where we're going to burn the fuel. This is going to get really hot and push this down. This is the piston. And the piston turns a crankshaft, and this goes around and eventually turns your tires. Okay? And so if we look at this, and the whole reason for the name four strokes is it'll go down, one stroke, up, two strokes, down again, three strokes, and return, four strokes, and then start the cycle all over again. Okay? And this idea was designed by burning gasoline, German guy named Otto. Otto, O-T-T-O, not Otto, A-U-T. I remember being a student. I think it took me weeks to figure out that the teacher was talking about a guy named Otto and not the automobile. But the nice thing is they go together. This is the automobile. This is called the Otto cycle. And here's how it works. Let's discuss it thermodynamically. But as I said, let's look at the internal mechanism. And it's pretty simple here. I'll start at, well, there's the end of it. Right here, this valve opens. We'll call that stroke number one, intake valve. What happens as this comes down, that valve's open and fuel and air go inside. Okay? So, intake valve. Here it goes, intake. Now, the valve's closed and we compress it, compression stroke. And as it compresses, of course, it starts to warm. And that's why the color changes here. Intake, and right here, compression, it's warming, small. Then the spark plug burns it. Spark plug makes a little spark, and the gasoline inside burns real quickly. All right? Now it is really, really hot. And so, here we come again. So intake, compress, burn, push down. That's the power stroke. That's the main point of the engine right there, the power stroke. You push those down. Now we've already burned all the fuel, so the last one is the exhaust stroke. There it is. Comes up, valve opens, goes out the tailpipe, we start again. Bring in fresh air and oxygen, squeeze it, burn it, push down, power stroke, come back up, send it out. Okay? And that's the internal mechanism. Let's look at that from a thermodynamic process and see what we come up with. Yeah?
Does some part of this engine rely on rotational momentum also?
Yes, so you have to notice of the 4 strokes, only one of them is pushing it, right? The power stroke. So the rest of the process comes from the momentum, the rotational momentum of the engine itself. And so that's why you'll have a flywheel on it. And that's why you will need a starter motor to get the thing started in the first place. And so you put the key in and you use the battery to turn it over to get things started. But once it gets started, this power stroke, right here, burning it down, the rest of this, pushing the gas out, sucking more in, and this is a hard one, compressing the gas. That is always slowing the engine down. Now, fortunately, we usually have multiple pistons if this is a car. So, you know, if you have a 4-stroke, or a 4-bang or 4 cylinders, one of them at one instant is involved into the power stroke. And so you spread out, you don't fire them all at one time. And you don't even fire them in a line, otherwise the engine goes, you fire this one and then this one and then the middle ones, yeah.
Is there some kind of mechanical process that opens the valve, or is it?
Yes.
Or is it a computer that opens the valve?
Well, it depends how old your car is. In the old days, it was all mechanical. That you would put this crankshaft that would then turn a camshaft, so there would be a chain or a belt, and the rotation of that would open and close these valves. So, yeah, so there's a lot going on inside of that engine. Today, you can open the valve with magnetics, electromagnetics, and you can turn current into a coil and push and open the valves. And that's very helpful, because then you could open them a lot or a little or sooner or later and get the most efficiency. And without that, you wouldn't have cars as fuel efficient as they are today here. So. And fuel injection, yeah.
So is that why you don't typically see 4-stroke engines with less than 4 cylinders?
Oh, no. You do. My lawnmower's a 4-stroke engine, 1 piston. Yeah, my weed whacker's a 4-stroke. Now, my chainsaw is a 2-stroke. We'll talk about that one next. There's advantages and disadvantages of 4 strokes and 2 strokes. No. It would have to go all the way around. But again, you put a big heavy flywheel on the end of this, it's not a big problem. You push on it, and during the power stroke, it doesn't get going that fast because of the big heavy flywheel. And then that gives it enough, as you said, rotational momentum to carry it through the rest of the ones here. And so you don't have this, fast start between the 4 strokes. And then remember, this is 4, 5, 6,000 RPMs too. So there's not much time really between the firing and the firing again and the firing again. But you'll definitely notice the vibrations, if you're holding the, like I said, my weed whacker. Well, as I said, we should then use our information. We won't really talk about entropy quite yet here. But if I were to come over here and say, okay, let's try to solve this problem with thermodynamics here. This was the original design of the gasoline engine here. And as you pointed out, it is much more complicated than our simple model is going to work with. But let's look at what we'll call the Otto cycle here. Let's draw then a PV diagram here. And so as this is going around, I will kind of label this as, and your author labels the larger volume as V1 and the smaller volume as V2. And so in this picture you can kind of see that as it goes up and down, there is a time where it's down here, so that would be the bigger volume, volume 1. And there is a time when it is up there, so that's the smaller volume, V2. And there's something else in between it. So I'm going to just put kind of a dotted line up here. And note that what takes place is somewhere between there. Let's start at the beginning. Let's start at what I would call the intake stroke. What's going on in the intake? Well, on the intake, which is coming right here, here we go, this valve opens, and what happens is we're letting in a lot of fuel, a lot of oxygen. The valve is open. I would say at that point, the air is coming in because of the atmospheric pressure. It is roughly isobaric, right? And so what happens is I would go, say, from here to there. And the volume of the gas is getting bigger, but the pressure isn't changing. Fair enough? Yeah.
Is that because the piston is moving down in a way, so you're getting an increase?
Right, so the piston's moving down,
And then you have the air pressure pushing
and then the air pressure pushing it in, right? Right.
And they roughly.
And obviously for the air to come in, when piston goes down, it's going to have to be a little bit lower than air pressure. So you could argue that it dips down. But for simplicity, right, we're going to overly simplify reality here, so we have something to work with. And we wouldn't want it to be too hard with the test coming up. And we wouldn't have anything for you to do next year when you transfer. So we got to leave something up there, yeah. Yeah.
Wait, is this intake is technically doing work because it's expanding and because on the part right there, it's doing work.
Okay, you certainly could. It is expanding. You could view it down here. As this comes down, doesn't it have to push these molecules out of the way? So it is doing work. It's got to push the atmosphere back. Sure. Well, fortunately, we'll get a lot more when we burn the fuel than it took to open that. But let's keep going through this. Let's call this point A here. This is really where the thermodynamics gets interesting, because what happens after the intake stroke? Well, after the intake stroke, the valve up there closes and it compresses it. Now again, this could be 2,000, 3,000, 4,000, 6,000 RPMs. Now I know this isn't perfect, but I would say that gets compressed back to volume 2. The pressure goes way up. I'll call this point B, but what kind of process would I roughly call this? Adiabatic. Yeah, good. And I'd call this the adiabatic process. And so that compression stroke right there is adiabatic. Even put compression. And so that's how I got to B. All right, now watch what happens. As we compress the gas, here we go. So we open it, we compress the gas, we get up here, and all of a sudden now we burn it. Now I know it doesn't burn instantaneously, but again, overly simplify here. Let's just say it burns really, really quick. And that might not give time for the piston to move. Reality is it'll probably move a little bit. But roughly, what would happen is something that might look like this, right? The pressure would go way up. You've just heated it up here. In fact, this is the part of the thermodynamics where the energy goes in, right? This is where the energy comes from. This is the Q sub H. The burning of the fuel is where we're saying, okay, now we are putting energy into it. The analogy of what I did is this would be the moment where I did this. I put energy in. Although this one, I'm putting energy in and volume is changing. This one might happen so quickly that the volume doesn't give a chance to change. As I said, maybe a more realistic picture would kind of arch it over a little bit because it is going to expand. But for simplicity, let's just say it burns very quickly and I go from point B to point C. That's where I add energy. Yeah?
What process is this?
Well, it's not a stroke. It's right where the fuel burns. So it's at the top, what we call top dead center here. So here it comes, ready? It's this flash right there. Boom! So that's the spark. That's where everything gets real hot. Because then what happens? Yeah, this is the power stroke. This is the main part of this. This is where the piston gets pushed down. And so it goes down here. I will call that maybe point D. But again, what kind of process would you call that? Yeah, again, assuming it happens kind of quickly, it would be adiabatic, not having a chance to lose heat to the walls, which you know is totally unrealistic, because otherwise the motor would not be warming up here, right? And we know we have to put a water pump and a coolant to cool it down here. So again, overly simplified, but like I said, a good place to start. It's like, you know, ignoring air friction. It's not reality, but good place to start. And so during this power stroke right here, we go all the way down until we get to the volume. And then what happens finally? Well, I guess right here, the valve opens. Right there, opens. What would happen there? Yeah, then I would say as soon as that valve opens, the pressure drops very quickly. Right? And that's going to start getting gas to go rushing out. And then the exhaust stroke comes up and sends it back to its starting point. And so that would actually be the exhaust. And so, again, a little bit overly simplified, I realize, but at least it gives me something to talk about, something to work with, and a chance for you to hopefully see the real mechanics of the building of the engine and couple it together with the thermodynamics here of what's going on. Because as you guys were already asking here, this is a general discussion about efficiency. What would be the efficiency of this engine based upon this model? That again is overly simplified, I realize, because you know a real engine will probably curl this way. So anything that is going to make this area bigger, the way I open the valves, when I open the valve, how I close those valves, all of those are going to make one engine more efficient over another. But if we kind of lump all the engines together in this kind of block diagram, what is a bigger overarching picture of an engine other than the individual pieces of designs that different companies and different engineers will use? That's what I want you to see.
So the QC is going to come out on the exhaust.
Yeah, so again, it's a little bit hard to really put on a simple PV diagram because we're actually changing the molecules. We actually burn them, then we let them out. And so I would call the QC coming out at this point, but it's also this point too, because all I'm doing is whatever heat is left, I don't really take it out of the molecules themselves. I just get rid of the molecules. And so that's what comes out the tailpipe. So this whole process from here to here is the QC. I get rid of some energy as it comes out the tailpipe. And that's why many people today are thinking about, you know, maybe we should harness that energy that comes in. Because it's not there's not a lack of energy there. There's a lot of heat. If you've ever accidentally touched the tailpipe, there's a lot of energy there. And so we probably could harness and do a lot more things with it. Right, and the turbocharger is an example of that. Sure. Yeah.
Can you show on the diagram what part D to A is?
D to A is right when the exhaust valve opens. So here it comes, ready? We burn it, and right when that valve opens, the pressure is going to drop really quick without the volume changing. Okay. So the piston's down there and the valve opens, and it just, the gases start going out, and the piston hasn't gone up yet.
Okay.
So this is the valve opening. This is now the piston moving up and then getting rid of the rest of the heat and what's ever left. Yeah.
Why do we only see turbos on cars that are designed for performance and not just cars that are made for efficiency?
Turbos don't add efficiency. and you can run the exhaust off of it. But no, yeah, but no, but I guess the answer is when you restrict the flow of the exhaust gases coming out of the tailpipe, okay, you hurt yourself in this part right here. You see this part where it's going up and exhausting? If you've got to shove those molecules out, and so anything that builds up pressure in there really hurts in here. And turbines are very high maintenance. Changing the oil a lot, very expensive. So I don't think anybody's really come with a good use of the exhaust fuel. I think better thing is to turn the heat into electrical. That would be my approach. A thermoelectric effect, and turn the heat into electricity and use electricity to run, say, more electric motors or something.
A turbo wouldn't increase the efficiency of any given motor, but it uses a smaller motor to accomplish the same task, right?
Because it increases the volumetric efficiency.
Yeah.
So you, instead of having a standard 1.2 liter in your super efficient car, you could drop it down to a smaller motor that would have enough power to do what you need to do.
But don't
Okay.
have problems with engine life because they create a lot of pressure and heat?
Yeah, see, the back pressure that you get from them is just annoying. So it's a good discussion to have. But I don't think in practice anybody's really dealt with the issue of as this exhaust goes out, you get a back pressure. And that back pressure then, makes the engine itself work harder, less efficient, wears out sooner.
I think some companies have electronics in it to make it variable speeds. So
Okay.
So
Okay, and I don't know enough to say what companies are now doing with the turbos. It seems like there's a niche there that somebody could get something figured out, but I don't think it's there yet. I mean, you could argue the same thing, and in fact, I think we even had this discussion. I mean, the turbo engine itself, it can be really powerful and small, so why not put those in cars? I mean, you could never have like an Abrams tank or a helicopter fly like we do today without putting a turbo engine in it. I mean, it would be impossible. But the maintenance on it, I mean, certainly not as like the Abrams tank. I think the maintenance on a tank is, you have to maintain it more hours than you actually drive it. And nobody's going to want to work on their car more hours than they have to drive it. I mean, just taking it once a 6 months to get the oil change is a pain in the butt, right? So no, I don't know the complete answer. Well, people have tried different things, and I would think that there's an answer with this exhaust heat, and that's my point. But the turbos so far really haven't been all that great. The other issue of the turbo is if you're running on the exhaust, then that engine unfortunately is susceptible to the RPMs of the main engine itself. And that's kind of that turbo effect, at least of the old days, is where you would, if you wanted to go fast and you step on the gas, you don't really feel any effect from the turbo yet until the exhaust gases build up. Then you take off. And so there's this moment delay between stepping on the gas and accelerating. So, yeah. Well, anyways, I better keep going because there's so much math I want to say here. But you're right, there's a lot we could. And just looking at this, though, what would the thermodynamics be of this type of engine, the gasoline engine? So let's do our calculation. E, efficiency. As we had earlier, it is 1 minus the energy that goes into the cold side divided by the energy that comes out during the hot side. Now, the reason I went through this long discussion of this diagram here is this would be the heat coming in. The heat coming in is in a isovolumetric process. How do we calculate the heat in an isovolumetric process? Isn't that what we just learned in chapter 21? N CV delta T. And in this case, then, the delta T would be 1 minus N CV. What is my delta T? Well, I guess it would be the temperature at C minus the temperature at B. And so TC minus TB. And that would be this. If we go back to that picture, this is the temperature after the gasoline has burnt. This is the temperature before the gasoline is burning, but after it's been compressed. So it's already at a pretty high temperature because we compressed it, and then we're going to go even higher once we burned it. In the denominator, it would be NCV delta T also, but we are taking it out. Oh, I did that backwards, didn't I? Sorry. Yeah, this is the cold one. So D to A. And then this one is the hot one. And then the hot one is C to B. Right? And what makes it a little nice here is those cancel off. And so then I come up with, and again, I realize it is overly simplified, but it is the efficiency based on temperature, which really isn't that helpful because I don't know what temperature it is when it got compressed, and I don't know what temperature it is when it's burned. So let's try some more manipulation and get rid of temperature out of this equation.
Shouldn't that be TA minus TD?
Oh, fair enough. Absolute value. Yeah. So I changed the order so that I got a positive sign.
Oh.
Right. And that's why I said this discussion is absolute values. Yeah. Okay, now I'm going to leave this on the board here, but I'm also going to look closely here at point C and point D. You told me they were connected adiabatically. So, how is the pressure at C and the volume at C related to the pressure at D and the volume at D? Look familiar? That's the connection through this adiabatic process. So let me take advantage of that because I claim that by looking closely at this adiabatic process, I can rearrange an equation in temperature to an equation in volume. And that will be more useful. And so this is my connection. Now this has pressure and volume. Let's get rid of pressure. How do I get rid of pressure? Yeah, PV equals to nRT. So I can replace pressure with nRT at C over volume at C. And I can replace pressure at D with nRT over V. The N and the R cancel off. And in fact, this volume downstairs would cancel with one of the volume upstairs. And the same thing on the right-hand side. And so this adiabatic process that we were doing in the last chapter, which connected pressure and volume, can also connect temperature and volume. And that's great because I have an equation that has temperature that I would like to get rid of. So let me use this relationship of the temperatures to get rid of this formula that has temperature, and then I'll have a formula with volumes. And like I said, that will be a more interesting approach. So let's also look at B to A. How are B and A connected? They're adiabatic also. So if I connect them adiabatically, I would have the temperature at B times the volume at B, gamma minus 1. And then I would have the temperature at A times the volume at A, gamma minus 1. Fair enough? And maybe I'll just take these two equations and write them over here. The volume at C is what we're calling volume 2. So I could write this as temperature at C, volume at number 2, that's the smaller volume, gamma minus 1, equals the temperature at D times the volume at D. Now, the volume at D is what I'm calling volume number 1. So this would be volume number 1, gamma minus 1. The equation below that, we can do the same thing here. This would be temperature at B, this would be temperature at A. This would be volume at B, but volume at B is number 2. And the volume at A is volume number 1. And so now you can see this sides have the same volume. So if you take these two equations and you subtract one from the other, this says Tc minus Tb times volume number 2, gamma minus 1, equals temperature at D minus temperature at A, volume at 1, gamma minus 1. And when we rearrange it, temperature at D minus temperature at A over temperature at C minus temperature at B, that's what I'd like to solve for, there it is, would be the volume at number 2 divided by the volume at number 1 raised to gamma minus 1. Yay! And so I have got the answer of what I was looking for. What is the efficiency of an internal combustion engine? It is 1 minus V2 over V1 gamma minus 1. At least, as I said, in the sense that we have an idealized engine, the valves open and close, the mechanics work without friction, and all these other things that are really unrealistic. But putting all those aside, then every engine would operate with this efficiency, and it's based upon what? What we call the compression ratio. How big is volume 1 compared to volume number 2? In this picture, we are probably looking at an efficiency of, I don't know, 8 to 1. Typical numbers for engines, 8 to 1, 9 to 1. It's hard to get it much more than that. Things are getting smaller, pressures are getting higher, temperatures are getting higher, things leak. But those are typical operations of an engine, 8 to 1, 9 to 1, yeah.
So that's why diesel engines are as high as 22 to 25 to 1.
Okay, now, yeah, we'll do a diesel engine next here. But you can see then that if you want it to be more efficient, one of the first things you would do is just increase the compression ratio. That alone leads you right down the road of more efficient, more efficient, more efficient. Yeah, and so diesel engines have like 25 to 1, you know. And for other reasons too, we'll mention in just a second. But that makes them real, real efficient. Of course, these valves have to open and close, so you got to get room for them to open. So getting too big of a ratio can be problematic. Fortunately, they open when the piston's down, so that's good until something goes wrong. Then the piston comes up when the valve is open and whole engine gets damaged. I guess they call those interferent engines. Yeah, high efficiency, but potentially really problematic. Anyways, but that, as I said, is the Otto cycle. In fact, as long as we're here, we might as well look at something very similar to this. I've been focusing on the 4-stroke engine for obvious reasons. It's the most common one. Here's a good internal working of a 2-stroke engine. It essentially does the same thing, so there's nothing new in terms of the thermodynamics here. But what's really nice about a 2-stroke engine is how much power you can get in a small space, and how few moving parts you can actually have. Of course, the bad thing is it can really pollute and be very noisy. And if you look carefully at it, it's kind of a clever design. Every time the piston goes up, it fires. Brings in more fuel, compresses it, fires. Brings in more fuel, compresses it, fires. And so it's firing twice as often. So that alone, you can get twice as much power for the same size. And so, you know, you're going to put this in a chainsaw, great idea. You know, you want that chainsaw as light as possible and as powerful as possible. And that's a good approach, that 2-stroke engine. Oh, but look at some of the other non-moving parts here. It's kind of, it's a great design, this is the fuel in the air in the blue again. You're actually using the moving piston as the pump. When this goes up, you can kind of see that this flows into this area. And as it comes down, it squeezes it so that it goes in. When it comes down and this gets past here, there's your new fuel. So there's no valve to open. It just goes down here. Also, there's no exhaust valve. This just comes down, and when it gets to here, it goes out. Unfortunately, not all of it goes out. Unfortunately, as this rushes in, some unburnt fuel goes out. And so we don't get a nice, clean, new mixture. We don't get nice, clean, burnt air out the other side. So powerful, yes. Polluting, yes. That's causing an effect here. But you don't have the valve to open. You don't have the weight and the, as you said, the camshaft to make the valves open and close, or the other electronics that are needed. It's really, really simple. You can even cut down on the oil pump if you do this fuel and you mix oil in the fuel itself. And so as the oil comes in with the fuel, the oil will kind of splash around in here and lubricate all your parts. And so we don't need to pump the oil through there. We don't need to change the oil. All kinds of great things.
Does that scale to a larger rotor, like a V8?
Oh, yeah. Yeah. So, again, if you didn't mind polluting the world, and so they're very illegal in California. I had a hard time finding a two-stroke engine on my weed whacker. I don't think you can anymore. They're not legal. You still get them on the chainsaws because, Oh, you can? You can? Ah. All I know is I went online to buy my weed whacker, and it said can't ship to California. What? So, tempted to send it to my parents in Arizona and then go pick it up. But I kind of like the idea of not having to mix the fuel. It wasn't that the fuel, and then I go, yeah, I'll just get a 4-stroke. Costs more, but. Well, again, now putting on a catalytic converter like the turbo is you reduce the airflow. And you reduce the airflow, you lose the efficiency. And so, maybe what you save by not polluting, you now pollute because you burn more fuel. But you don't. I mean, in the original catalytic converters were a big pain. I mean, we don't think about it much today, but when the catalytic converters came out, I mean, it was a very controversial issue, You want lower fuel economy? Cost you more for your fuel? Less power in your car? Or you want clean air? I mean, the debate hasn't changed, but, now they're different, Do we want clean water? It goes on and on. But the catalytic converter was a big controversy. California still has that. I mean, we've got the special gasolines, and no place else in the country, maybe New York does, but we've got the special summer blend. So we pay 50 cents more than any place else, in the nation. That's what we pay for,
Why can't you make a two-stroke where you don't have to mix the oil?
Well, you could, but now you would have to have a fuel pump. I mean, oil pump. Which the whole point of this was to get it light. Powerful and light. If you're not...
I feel like you're getting a power stroke every 2 strokes instead of every... Yeah, but it's not twice as powerful because you don't get a nice, clean, new fuel. So you don't get twice as much power. You get like 1.5 times the power. Yeah. But there's your two-stroke engine, if you will. And actually, Mazda did this one in their RX-7 and their RX-8. The rotary engine is kind of an interesting design. It's never really quite caught on, but I remember in the 70s, like, oh, this is the motor of the future. It's going to take over the world. Unfortunately, they've had so many mechanical problems of it. But look at this. This thing has 3 power strokes in 1 revolution. Not just 1 power like the 2-stroke per revolution. And the 4-stroke only had a half a power for 1 revolution. We had to go 2 revolutions before we fired the gasoline. This thing fires 3 times for every 1 revolution. Crazy design. Look at the shape of this thing. So the fuel comes in here, fills this chamber, gets compressed, gets ignited right here, expands and rotates this crazy triangle, and then sends it out here, kind of like that 2-stroke engine.
So many gears and moving parts.
And vibrations that don't last long. But you talk about a lot of power in a little space. And the fact that it's rotating, because you think about the engine, we make things go up and down only to eventually change that to a rotation. And so there's a lot to be said here. And wouldn't surprise me if, you know, it continues to make a big comeback in the future here. But this rotary motor has, you know, done it good.
Because of material science problems, looking at it just now, like the only thing that looks like that would fail is that the corners would eventually wear out, and you would have a useless thing where you never have any compression. So at point A, when it goes, eventually point A wore down after like 5 years.
Right, and the shaking
Yeah.
and the unbalanced. If it's slightly unbalanced, it really shakes. So, yeah, so it's all about shaking and wearing out. Yeah. So yeah, so you overcome the complexity of the engineering. This has the physics potential of being quite useful. Yeah. Well, why don't we look at one more here? This is one I like to show people. It's so simple. It's a Stirling motor. And if I just make one place hot and one side cold, and I should emphasize that, that's this whole part of a heat engine. The heat engine is making the heat energy flow from one side to another. Now, we haven't got a chance yet to talk much about entropy, but the entropy part of it says that nature will take it from hot to cold. So anytime you have something hot and cold, as simple as some people are working with is laptop computers. I mean, the warmness of your lap is enough to make enough electricity between that and the room to run the computer. And so why have a battery? Why charge a battery? Just put the laptop on your lap and get enough heat. In fact, I should bring that model out. It's not that doesn't fall in the category necessarily of heat motors as we're using them, so I didn't bring that one out. But I should remind me to show you that one. I should show you that one. But I like this Stirling engine because here, if you look closely at it, this is going to be the spinning part in just a second. And what's going to happen is I'm going to cool the bottom and the top is going to stay room temperature. And so it looks something like this as I place it up here. This is going to be cold, this is going to be hot. Notice this thing right here. It's called a displacer. And from your vantage point, you could probably see it go up and down when it spins. It's just a piece of foam and it's designed to displace the air. It's made out of foam because we're lifting it up, we don't want it to be heavy. But it's got to be something that's displaced the air that's not heavy. And so as it goes around, it is displacing the air. Now watch what happens when the displacer is, say, here. The molecules are near the cold side. Or here, the molecules are near the hot side. Cold side. Hot side. Cold side. Right? And so as the displacer goes up and down, it displaces the molecules. Now watch what happens when the molecules are near the hot side. They're going to get hot. When they get hot, they go faster, right? More pressure. Now, this is going to be the piston. This is what's going to get pushed. Now, it doesn't show it in our diagram here. Right now, I have a piston and it's kind of bolted into place. And so all that happens now is when the displacer comes back down to here, the molecules go here, they get hot, and they push on this. But if you take these bolts off, that would push it. And then when the displacer moves up here and the molecules get cold, then the molecules on this side would push the piston back. And we can use the hot and cold. Yeah, I don't think that was starting quite yet. But it doesn't take long. Oh, I even pushed it the wrong way. But there's the Stirling engine. And if we add to our little model, you can kind of see it here. Here's the next picture in our diagram that we take the hot and cold. And this is what I was thinking earlier might be a good approach to the exhaust gases and the radiator in the car, is to let the piston move. And of course, to finish our picture, we've got to connect them together. So as the gases push the piston, They will also be connected with a chain or a rope here, so it'll move the displacer. Of course, you also want to connect this to something because you want something to move. So in this model, you can kind of see that the piston is this one here. It gets pushed up. That makes this thing move. Also connected to it is the displacer, and so that one there is making the displacer. So the force from this piston does, the rest of the mechanical part, getting the displacer in the right position at the right timing. And so timing is important here. But we can, make a little motion out of this. And again, this would be under this category of a heat engine. And so, that's a good question. Where would you find good example of a Stirling engine?
Stirling engine generators for yachts.
Oh. Okay, yeah, I have too. Now that's a good example. On the deck of a ship, you would use the sunlight. You would use that to heat one side of a metal bar, and the other is hopefully cool from the ocean breeze. And then you turn that, which turns your generator, which charges your batteries for that night. I know they're experimenting a lot with this, again, for alternative energies out in our desert here. I think they're actually starting to build one in the Arizona desert where they just set it up and then they use the heat. The heat turns a Stirling engine. The Stirling engine turns a magnet. The magnet makes the electricity. Yeah.
What starts the displacer?
Well, if you notice, I had to give it a little nudge to get it started. So just like the gasoline engine, I got to turn the key and use the electrical battery to do an electric motor to turn it to get it started. But once it starts moving, everything continues on its own. Same thing here. I gave it a little nudge. I actually nudged it the wrong way. I'll stop it. And if I get it in that position, it's not going to do anything. Okay? But if I put it somewhere where the piston is already compressed a little bit, then the heat's going to push it up, and then the momentum will continue it through its process. So it just need that little nudge to get started, and then it works just fine. Again, just like your gasoline engine, you get a little chemical energy from your battery, boom, and now you can run the car for 20 miles, well, hundreds of miles before worrying about it again. Yeah.
Are Stirling engines very weak or very strong?
Well, okay, now the strength of them, of course, is now going to depend upon, of course, how many molecules, so how big is it, as well as that temperature difference. This one is not going to be very powerful. It is only operating between 20 degrees Celsius. In fact, this one's kind of neat. It's designed to operate in your hand. I mean, this one's going pretty fast because I put it on ice. But if I just hold it in my hand, the heat of my hand being a couple degrees warmer than the air, it will turn on its own, just from body heat.
So will a Stirling engine, in most cases, be weaker than like a gasoline engine because you don't have the pressure increasing immediately because of combustion, and you don't have extra energy being used. That up a slow process.
Yeah. I mean, that burning of the fuel is amazing.
Yeah.
So you got to get it really hot, but a good solar dish, like on the yacht, or a good solar dish in the Arizona desert, you can capture a lot of sunlight and focus it into a point. And you probably burnt paper. You can burn paper. You can get things really hot. But again, the power is really based on how warm you're going to get it.
Because it's more passive.
But again, how warm are you going to get it? You could over here. You could actually burn. I mean, many of these. Yeah. And actually, I saw a Stirling engine on a ranch one time. The farmer was doing this. The farmer had a lot of hay, and had a farm that was in a low nutrient area. So what he did is he got himself a Stirling engine, and he made a metal bar. Okay, and he put all the hay. And the hay just heated one side of the bar. So between the hot bar and the cold air, that would turn the Stirling engine. And what he did with the Stirling engine is he made go around, and all it made was a hammer. But he took rocks out of his field and he put them under the hammer. So it crushed the rocks into powder. Then, when he spreaded his seed, he would spread the crushed rock, and that's how he added nutrients back to his field. So he got a cheap price on the land because there was no nutrients. And then he got a cheap price on the engine, built the old hay, and that was his approach. I don't know how successful he's been, but that was his business approach. Yeah, yeah.
Could you explain how this displacer goes up once it's on the pool side?
Well, the displacer is only moving because of the gears are hooked together. So the hot gas pushes this down, which turns that wheel. That wheel turns this wheel, which then pushes the displacer up. So the displacer is not moved from the gas. The gases move the piston, which move the wheel, which move the wheel, which move the displacer. And the movement of the displacer changes the position of the molecules, which then keeps the process going. Well, one last one here, and I suppose we better continue on. Where is, here is a diesel engine. If we make the top of it flat, we can get much higher compression ratios. And as it comes up, we essentially have the same thing, except right here, here's the exhaust valve, so we push it out, okay? And watch this, here comes in our fresh. And as we squeeze right here, and if we squeeze this 25-to-1 ratio, that can get hard enough to ignite fuel. And so while we were talking, I go, hey, I'll throw this one in here again. I know we saw it once, but it's, I think, worth seeing again. Because really, an important difference between the diesel engine and the gasoline engine is you don't have the spark plug. Why not? Right, because this is getting so hot, it will combust on its own here. And so again, as you already saw before, if I were to push this down, I would get it very hot, and it would combust on its own. Now, that also means a little subtlety here, is as you're compressing it, you better make sure there's no fuel in there. Because you'll get halfway down and the fuel will ignite and start to push it back before it can get to its top and come around. So an important part here is that you have a fuel injector, and so that's what this little added piece is right here. And so as this comes in, this fires it. But it makes the PV diagram very different and much more efficient, as I'll hopefully show you, but not too much because it's a homework problem. I'll let you work out the numbers on it. Yeah.
Why can't we do that with the gasoline engine?
I guess I'm not following you. We are, except we're not getting it hot enough to ignite the...
We have the high compression ratio with the gas.
Oh!
Fire.
Well, you... I guess what you're...
Gasoline's also less dense. And it seems like in gas engines we're always limited by our compression. And you said higher compression is higher efficiency. So why not just bump it up?
Yeah, but remember this too. The fuel cannot be in the chamber while you're compressing it.
Well, we can have a direct compression.
Yeah, I know. I knew you were going to say that. So that's where I'm like, I suppose we could. But now we're getting to a... This would be my answer, and my guess at the answer is, now we got to be careful injecting gasoline into a hot environment because gasoline burns so much easier than diesel fuel. And I think that's the problem you're going to run into. Diesel is hard to ignite. I mean, you could pour diesel fuel on the ground and put a match on it and it won't light. Don't try it, but it won't. Whereas gasoline will blow up in your face. And so I'm thinking that might be the problem of the engineering is we're trying to inject fuel that's very volatile into a hot environment. We can't control it well.
So it doesn't burn, it explodes.
Well, you're right. It seems like I could probably build something like this where I'm injecting either a gasoline or an alcohol. I just have to make sure I'm injecting it. It can't be in there ahead of time, that's for sure.
Right.
That's for sure, yeah.
Wait, so the blue air is actually air, not actually fuel? It's just...
So right there, it's compressed. Well, no, right here.
Like the blue.
Yeah, so this is just air. Just air. Now we inject the fuel. Okay, and so the injection. And it makes the PV diagram a little bit different here, as I want to show you. Yeah?
On a diesel truck, there's like this little, well, one of them anyway, there's like this little coil thing on the dashboard that you have to wait for to when you start it. What is?
Oh, okay. Now, yeah, the compression that I'm talking about warms it, but also the warm engine helps warm it. So in other words, when you go to start your car, you actually have a glow head. You actually have a heating element in there that you're waiting for. Yeah, so you got to wait for it to warm up a little bit first, just because if it's particularly, you know, if it's a cold morning and you take the air in and you compress it 25 to 1, it's not enough to ignite the diesel fuel. So you got to wait for that to warm up. And that's what that part of it is. Yeah. Well, here's the PV diagram. Let me not take the time to go through the same mathematics for efficiency, but let you do it for a homework problem. But here would be the PV cycle. It would look a lot the same in the sense that you would let air in, you would compress it. Here's what's very different though. On the Otto cycle, what we said is we put in, the fuel's already in, we ignite the spark plug, we modeled it as a constant volume. It was not perfectly a constant volume, of course. In reality, it probably arched over a little bit, and that's why a real engine will probably have less efficiency, quite a bit less efficiency than this idealized model, but nonetheless, that's how we modeled it. What is really nice about the pressure fuel injection here is that fuel injection is set at a certain pressure. The fuel is at a certain pressure. So as you eject fuel into it and the pressure builds up, if the pressure gets too high, it won't let more fuel in. The fuel is stopped because of the high pressure. And so, as you are burning it, as it is expanding, as the piston is going down, only as the pressure drops does more fuel go in to burn it to keep the pressure at a constant pressure. And that's the important difference here in our diagram. That we would then, as we are burning the fuel, have a constant pressure, not a constant volume. And so you're asked to kind of go through the math and to find the efficiency of an engine that looks like that. All right, well, boy, all that took a lot longer than I thought it might, but it was good. Let me jump back over here to a fun one that's not exactly a useful one because it would take so slow, but theoretically is a good one to discuss because it shows us all the physics of what's going on, and it's called the Carnot cycle. And so Carnot said, what if you built an engine that did something like this, where as it goes through its different steps, you match all your temperatures and pressures just right, which means you have to let things go real slow. And so that's why I said there is no such thing as a Carnot engine that we're going to build, but we are going to see that this is the most efficient anything can get. And so, as you probably know, we often improve our efficiency as we sacrifice power. And so this very slow process is the most efficient we can get and still obey the first and second law of thermodynamics here. Let's look at this one and see if we have enough time to calculate its efficiency. Here's the process. Here's a PV diagram, and if we start here at point A, it might look something like this. Point A has a small volume, so I will push the volume, whoops. Let me cool it down a little bit here. Let me get some air in it. Maybe I will start it here. And I don't think I can actually follow that cycle, but I'll roughly follow it so you'll see what's going on. So starting at A, which says small volume, so I'll push it down and clamp it. And it also says high pressure and high temperature. So this will be my starting point right here. Okay? And so point A is at this, where I am at a high pressure, small volume, and the temperature is along this isotherm. And what we do is we let it expand isothermically. And so the first process is an isothermic expansion. So if I hold it down here, so it can't go up, and loosen the clamp, if I let it come up, and I do it slowly, because if I did it fast, its temperature would go down, right? But if I do it slowly, its temperature is trying to go down, but doesn't get warmed up because this is sitting in here. So if I come up about halfway, maybe right about there, and I'll clamp it to stop there, I have done A to B. Heat has gone into my system. And so this is the Carnot cycle, or at least the beginning part of it. From here to here, temperature is equal to a constant. In order for the temperature to be a constant, heat has to go into it. But then I have to let it expand. And so this is the adiabatic part. So I'm going to take it out. I'm going to wrap it in some insulating material so it can't get cooled or warmed from the room. And I will release it, and it will hopefully go up even more. And so as it expands, it will be cooling. Now, if it expanded enough until it cools to the ice water, then me putting it here in the ice water wouldn't change anything. Of course, I didn't get it to expand that much, so I'm going to clamp it and put it in the ice water. Okay? But this part, the B to C, is the adiabatic. And so from here to there, B to C, Q equals 0. And then, during this part, I am going to let it cool down. I'm sorry, not cool down. It is already cold. I'm going to let the volume shrink. And so if I loosen that, it would shrink. Now I should have let it go slowly because I want it to shrink. Now if I did that fast, that would warm it up, right? But if I do it slowly, it tries to warm up, but it can't warm up because it is sitting in the ice water. And so as it sits in the ice water, the whole reason the temperature doesn't go up is because some heat comes out. And then finally, the last part, step D, back to A, is as it shrinks down, and again, I can't get it to happen exactly here, but had it shrunk down, I could then take it out of here, wrap it in some insulating material so it can't change heat, and then I can compress it more. And if I compress it enough, its temperature will go up in an adiabatic process, and it'll get back to A. And so there, Q would equal 0. And so this is a different cycle than we did for the Otto cycle or for the diesel cycle. We didn't really do the diesel cycle. But what would be the efficiency of this cycle? And as you soon see, this is worth discussing because this will tell us what the perfect efficiency would be. And when I say perfect, I don't mean 100%. Because I'll go back to the engine. Can you ever convert 100% of the heat into work? No, why not? Second law of thermodynamics, that entropy, which we haven't got a chance to talk too much about yet, but we're about to. We're going to run forward on time. But we can't and we don't ever expect to get 100% efficiency. That is impossible from the second law of thermodynamics. But there is a maximum efficiency, and we should design towards that. And we could ask, how close are we getting our engines to the maximum efficiency based on the second law of thermodynamics?
the source of the cold or heat goes away momentarily, why not just keep the cold there until the piston is all the way down and then apply heat and push the piston all the way back up?
Well,
That's supposed to heat go away.
could you build something like that? Yes. Okay, but, and I haven't really done the second law of thermodynamics, it won't be as efficient. And so this is the one that, as we look at the entropy here in a second, if we got time, we will see that this will be the most efficient we can ever get. So that's why I'm studying it. Not studying it because we're going to actually build this engine. It's a slow process, and the slow process is why it's so efficient. Okay? And so the closer we can get to that, but it gives us something to strive for. It gives us something to say, this is what we could do. How close can we get to that? And when I say could, we could get and still obey the second law of thermodynamics. Because to shoot for 100% efficiency is just a lack of knowledge about the laws of physics. That's impossible. But we can shoot for maximum efficiency. So what we're going to do is call this E sub C. Now the sub C, of course, is for the Carnot cycle, but that Carnot cycle is the maximum efficiency. I like to put it this way, as you just brought up. I'll just put EFF to save some time here, but the efficiency of a real engine, then, is going to be less than, or hopefully equal to, the efficiency of this Carnot engine, this Carnot cycle. And so that's why it's worth taking a moment to calculate what is the efficiency of a Carnot cycle. And I think we got just enough time to do it. I'll put here E for efficiency is 1 minus, and then it is the heat that goes in during the cold process divided by, or out during the cold process, divided by what is coming out, divided by what goes in the hot process. So this is the hot process, A to B, right? That is an isotherm. And so maybe it's worth going back a chapter, because you're probably still working on it. And actually, let me take this out before it gets too wet and I flood it and break it. Okay. But we learned how to calculate the heat in an isotherm. Notice this would be different than what we just did for the Otto cycle. The isotherm would look something like this. The change in energy is equal to Q times W. The E is a 0. So the Q plus the W are the same in magnitude. I know one's positive, one's negative. And what's nice about that is calculating the work during an isotherm was pretty easy. This was nRT dV over V, which then came out to be nRT natural log of final volume over initial volume, right? And since these then become the same, we can then say that the efficiency of this Carnot engine would be nRT natural log of, well, during the cold cycle, so that is a D to a C. This would be the volume at D divided by the volume at C. During the hot process, I should say cold, hot, down here, cold and hot, of course, would be a different temperature because I'm touching the cold versus the hot. But again, this would be the process as we went from A to B. You know, I guess I should be careful with my sign, because I think the way I have it written right now, that's a negative number, isn't it? Don't I want the bigger volume on top? So I'm going to put a C over a D. I know the formula we just worked out is final over initial. But remember, it says absolute value. And so absolute value means you have to have a ratio greater than 1 in the natural log, otherwise you get a negative. All right, so I'm going to change the order there so I've got an absolute value. Same thing can be said here for the heat during the hot process. This would be the volume at B over the volume at A. Now I don't know if this is so obvious, and we have a perfect moment to figure it out. But you might remember the adiabatic process we just did. The temperature that is connected during the adiabatic process, that means A to B, the temperature at A times the volume at A raised to A gamma minus 1 is equal to the temperature at B times the volume at B gamma over 1. Likewise, the other adiabatic process, the D and C, means the temperature at D, volume at D, gamma minus 1, and C, gamma minus 1, those have to be the same. And if you look closely here, C over D, well, maybe I'll just divide this crazy thing here. Okay. A, right, is the hot temperature. So this is T hot, then this is VA gamma minus 1. This B, oh crap. That's what you were laughing at, huh? I connected the wrong, those aren't adiabatic. Yeah. So A to D is connected. A to D is the adiabatic. What's the other adiabatic? B to C. Well, bummer. So I'm going to be out of time here, but a couple steps, you're going to see that the ratio of C to D is the same as the ratio B to A. Because isn't A and B the same temperature? Yeah. And isn't D and C the same? And so it may not be obvious until you sit down and do the math. But believe it or not, the ratio C to D is the same as B to A. So what does this become? And it simplifies, I think, quite amazing to an ideal efficiency. This is your ideal efficiency. Your ideal efficiency is based upon the temperature differential. If you know that you are operating at a cold temperature, such as the ocean water, okay? And so we go down here to Oxnard and we're going to make a heat engine that's going to turn a magnet to make our electricity. We know what this number is. We will crank this up as high as we can without melting our materials to get as much efficiency as we can. We really want to stoke that hot. And so we will, depending on what we're burning. In a nuclear power plant, we deliberately keep the temperature down. We don't even get close to the melting point of our materials, just in case something gets down. So nuclear ones tend to operate at a much lower efficiency. Yeah.
So we can calculate the maximum efficiency.